Embedded systems are the invisible force powering the devices we use every day. Smartphones, smartwatches, fitness trackers, smart speakers, and more. These systems are built to perform specific tasks with high reliability, efficiency, and often in real time. As technology continues to evolve, embedded systems are becoming even more advanced, reshaping the consumer electronics industry and improving the way we interact with our devices. There are several types of embedded systems, each serving a specific role. Standalone embedded systems work independently of other systems. Think of a digital camera. Real-time embedded systems are designed to process data and respond within strict time limits, such as anti-lock braking systems in cars. Networked embedded systems connect to other systems via wired or wireless networks, like smart thermostats that can be controlled through your phone. Mobile embedded systems, often found in portable devices like smartphones or tablets, are designed to be compact, battery-powered, and responsive. Creating an embedded system begins with requirement analysis, where developers define what the system needs to do, how it will interact with users, and what constraints it must operate under, like size, cost, or battery life. Once the requirements are clear, the next step is system design, where engineers map out the hardware and software architecture, selecting microcontrollers, sensors, and communication interfaces that will bring the system to life. Next comes hardware prototyping, where developers build a physical model of the device. This stage allows engineers to test components and connections in a real-world setup. At the same time, software development begins. This involves writing the code that tells the hardware what to do, using programming languages like C or C++, and integrating it with real-time operating systems to ensure speed and efficiency. Testing and debugging follow, which are essential to making sure the device works correctly and reliably. Unit testing checks individual software modules, integration testing verifies that modules work together, and system testing ensures the whole system performs as intended. Real-time testing confirms the system responds quickly enough, and hardware testing checks the durability and reliability of the physical components. Field testing puts the product into real-life situations to evaluate its performance under real use. Debugging happens throughout this process to fix errors in both hardware and software. Finally, the system moves into production and deployment. This involves scaling from a working prototype to full-scale manufacturing, with quality control procedures to ensure consistency. Logistics and distribution are also key here, making sure the finished products reach the market efficiently and on time. Throughout the development cycle, engineers face unique challenges. Many consumer electronics need to operate with low power, especially battery-powered devices. That's why techniques like voltage scaling and sleep modes are used to reduce energy use. Devices also need to be compact, which means balancing small form factors with performance and durability. Thermal management is another issue. Heat must be dissipated efficiently in tight spaces using heat sinks, thermal pads, and smart cooling designs. On the software side, real-time performance is a must. Systems like smartwatches or home assistants must respond immediately to user commands. This requires efficient code and fast, reliable processors. Memory is also limited in many devices, so developers use smart memory management techniques to get the most out of available space. Security is increasingly important. As more devices become connected to the internet, they face greater risk from cyber attacks. Encryption, secure booting, access control, and regular firmware updates are critical to keeping devices and user data safe. Integration is another major challenge. Hardware and software components must work smoothly together, which requires rigorous testing and debugging. Developers simulate real-world scenarios to catch edge cases and make sure the system performs reliably across a wide range of environments. Recent innovations have pushed embedded systems forward. New microcontrollers are more powerful and energy efficient. Multi-core processors allow devices to handle more tasks at once. Low-power chips like ARM's Cortex-M series let devices run longer on a single charge. The rise of the Internet of Things has also changed the game. Wireless technologies like Bluetooth, Wi-Fi, and Zigbee enable devices to communicate with each other and with cloud services. AI and machine learning are moving to the edge, allowing embedded systems to process data locally, react faster, and make real-time decisions, like a fitness tracker that adapts workouts based on your heart rate. The consumer electronics market continues to grow rapidly. Smartwatches, fitness trackers, AR glasses, and smart speakers are everywhere. In vehicles, we see more embedded features like infotainment systems and advanced driver assistance tools. Companies are investing heavily in research and development to stay competitive, add new features, and comply with regulatory standards for safety and privacy. Embedded systems are at the heart of modern innovation. They make our technology smarter, more efficient, and more connected. In healthcare, they power devices like pacemakers and insulin pumps. In agriculture, they control irrigation systems and soil sensors. In transportation, they help manage braking systems and engine control. In industrial settings, they automate machinery and track performance metrics. These fields could each be explored in greater depth as embedded systems continue to shape the future across all areas of life. If you're seeking expert engineering support and insights, follow us on social media to stay updated with our latest innovations and services.